Our conversation in calculus is going to start with limits, rates of change, and tangent lines. Calculus is divided into two branches, differential calculus and integral calculus. Now when we're talking about these two branches, we study them both in Calculus 1, Calc 2, and Calc 3. So we get an overview of both of those branches in Calc 1, and we just keep studying them more in depth from different angles and kind of looking at some different applications in both 2 and 3 dimension with different types of functions as we go through the calculus sequence. Calculus was developed in the 1600s to basically solve two big geometric problems. First of all, people were interested in finding the tangent line to curves. This is where differential calculus developed from. Integral calculus developed from trying to compute the area underneath a curve. Now we can find the area of a lot of basic geometric shapes like squares and circles and triangles and more complicated shapes than that even. But if we didn't have a nice geometric shape with the formula that was already developed, we're kind of stuck. And so we were interested in finding the areas underneath these types of curves. Now the applications have grown to cover a lot of areas. Science, industry, business, medicine, all sorts of different applications in calculus in all of those different areas. Both differential calculus and integral calculus rely on the concept of a limit. And so we're going to be studying limits starting in section 2.1, but we're going to really kind of get into the meat and potatoes of the limits in section 2.3. Starting about limits, rates of change, and oftentimes rates of change is abbreviated ROC, and tangent lines is kind of a good way to step into calculus. The first thing that we want to look at more in depth of is rates of change, and again oftentimes we abbreviate rates of change with ROC. Rates of change basically is the relationship between two changing quantities. Now basically these can be any changing quantities, but typically distance comes into mind, an infection rate in a population, an interest rate per year. Those are some different types of rates of change. One that we really like to look at a lot is velocity. Now with velocity, we're basically looking at the rate of change of position with respect to time. So again, velocity, the rate of change of position with respect to time. A lot of times we end up using WRT as an abbreviation for with respect to. We also talked about infection rates of a disease like the swine flu or the bird flu or flu, just in general, flu season coming up, and also interest rates. Now interest rates are of interest because of course we like to earn some interest on our money. Okay, but they're also of interest because of the high interest rates that credit card companies also charge. So let's go ahead and look at a little bit more specifically what rates of change look at. In talking about rates of change, basically if x and y are related somehow, the rate of change tells us how much y changes in response to a unit change in x. But this only works when rate of change is constant. So if we can apply this to a vehicle, let's say, driving down the road, we're talking about the rate of change, how much y changes in response to a unit change in x, how much our distance changes per hour. So that's our unit change. But when we're talking about this, this only applies when the rate of change is constant. And the reality of the situation is that oftentimes we're speeding up and slowing down. We're not always moving at a constant rate of change. Again, if we were going to assume constant velocity, which of course we know is not always valid, we use the time and true formula, distance equals rate times time. We use this for everything. We solve for distance, we solve for rate, we solve for time. But if velocity is changing, this formula does not apply. So what do we do then? Well, what we do is we use some calculus. But for now, let's go ahead and look at a quick example. If we were driving for 4 hours at 75 miles per hour, we could determine that our distance traveled was equal to our rate of 75 miles per hour times our time of 4 hours, and we would have traveled for 300 miles. But again, we're assuming that we're going a constant rate of 75 miles per hour here, which doesn't really make sense because of course we can speed up and slow down, so the 75 miles per hour might be an average or a typical speed. So again, what do we do? If the velocity is changing, what if it's increasing and decreasing? What should we do? And the answer is we will use calculus to solve these types of problems. Next, we're going to look at just kind of a general idea of what a tangent line is. We can't really talk about a tangent line too specifically yet because we want to have more of a mathematical description of a tangent line rather than a description that you might have gotten, from a grade school definition where we're talking about, oh, a tangent line touches a circle one time. That was kind of a general definition that we had. Well, a tangent line here is pretty easy to note that that is a tangent line. It does touch the circle once. This tangent line is pretty nice to look at on the parabola. It touches the parabola once. This tangent line is nice to look at on the third degree polynomial curve that we have here. Touches the graph once. But what about this particular line? It touches the graph once, but we have an intuitive idea that no, that's not really a tangent line. So what we have here that is, yes, this is a tangent line to a parabola, tangent line to a curve, but this one is not a tangent line. And why is that? It's touching the curve once, but if you note, it's not skimming the curve like the other ones are. So for right now, when we're talking about a tangent line in general is a line that skims a curve. And again, we'll develop this definition a little bit more later on, but for now that's kind of how we want to look at it. Our next topic of conversation will be velocity. And we've already mentioned velocity before in terms of infection rates, how fast something is going, the rate of change of position with respect to time. Interest rates were another rate of change. But we want to look at a couple different types of velocity. First of all, let's go ahead and look at instantaneous velocity. Now, instantaneous velocity is basically describing the speed and direction of an object at a particular moment. Instantaneous velocity is kind of hard to look at. If we use the old distance, rate, and time formula, we could solve for rate, and we get rate is equal to distance divided by time. Except without calculus, there's really no good, easy way to come up with the formula for instantaneous velocity, and we want to develop that eventually. So this is no easy definition without calculus. We can start to develop the concept of instantaneous velocity, though, with a concept called average velocity. Now for average velocity, what we can do is kind of follow off of that formula, distance equals rate times time, and if we solve for rate, I get rate is equal to distance over time. Now again, kind of working from the same idea when I'm talking about average velocity, my rate is going to be defined by distance over time. Distance is defined by change in position over change in time, and of course the delta is the Greek letter delta there means change, so change in position over change in time. So let's go ahead and look at an example where we're looking at some average velocity. So here for this example, let's go ahead and suppose, and this symbol right here, the S with the P hanging from it, means suppose. Suppose we have an initial position S naught of 0. That's a nice initial position to start with. It makes our calculations easier. We have a final position in this particular case of S1, our position at 5 hours into the movement of 150 miles. Initial time T naught is 0. Final time that we're looking at here is T1 is 5 hours. So let's go ahead and find the average velocity. Now when we're looking at the average velocity here, we can come right back up here and look at this formula. Change in position over the change in time. Well, often s is used as a position function. So a lot of times if you see s of t, it means position at time t. So again, we're going to use s for our position function here. So this means change in position over the change in time. Well, change in position is your final position minus your initial position, your final time minus your initial time. So for this particular case, that would be 150 miles minus 0 miles, 5 hours minus 0 hours, which leaves me with 30 miles per hour. Now this is very intuitive. This is how we work problems anyway, so that this is not shocking or difficult, and we certainly didn't use any calculus here. However, at any given moment, the car may be going faster or slower than 30 miles per hour. This is only the average. So another interesting thing to think about is our initial position was at 0. We drove 150 miles to our final destination. During that time, our average rate of speed, or our average velocity, was 30 miles per hour. Sometimes you were going slower, sometimes we were going faster. Unfortunately, we can't find instantaneous velocity with this particular formula. And you might say, okay, well, why can't you find instantaneous velocity with this formula? Well, because what ends up happening with instantaneous velocity is at a very instant, our initial and our terminal time is going to be equal. So when we take this denominator up here, t1 minus t naught, I get t1 minus t naught equals 0. Putting into our formula, that would imply here that we have some number divided by 0, which of course is undefined. So that's why I cannot use this formula to find instantaneous velocity. We should be able to get a good estimate of instantaneous velocity by using a very small time interval to compute average velocity. So for instance, instead of taking our average velocity over 5 hours like we did up above, maybe we would estimate our instantaneous velocity by taking our average velocity formula over a 2-second interval, or maybe a 1-second interval, or even smaller than that. So again, a good estimate of instantaneous velocity can be found by using very, very small time intervals and computing the average velocity on that very small time interval. Now remember, average velocity is your change in position over your change in time, and the smaller your interval of the change in time, the better estimate it is of your instantaneous velocity. And what this would look like, of course, is just our average velocity formula, change in position over the change in time, over a very small time interval. Now, what did Galileo have to say about the velocity thing? Well, he surmised that if an object is released at t equals 0 from a state of rest, and that means you're not hurling it like you would a baseball, but you're just dropping it from a static position toward the ground. So if you dropped it from a state of rest, the distance traveled after t seconds is given by the position formula s of t equals 16t squared. And again, s of t is our position function. 16t squared gives the distance traveled after t seconds. Now if you drop something from a 100-foot tower, s of t at a particular time will give you the distance traveled between 0 and 100 feet, because clearly it can't travel any more than that. But this is just one of the many possible functions that we can use to estimate some things like these. So again, this is just one of many functions. And this takes into effect gravity. Meters per second would be a little bit different formula because the 16 is based on feet per second. This is just one of many functions that can be used for this purpose. Let's go ahead and look at an example that has